Thank you again for a brief introduction, Mr. Chu. So again, I'm Roel. You can call me Roel, but Mr. Chu always like to call me Professor. And when he called me Professor, I remember the heist movie, the professor who planned the bank heist. There's a TV series in Netflix. So actually, it's better to just call my name. Yeah, I'm with UTP for the last 4 years. So today it's a continuation of our discussion last month. But this time we'll focus on membrane bioreactor for industrial wastewater treatment. Okay, so this is the outline of my presentation today. So we'll start with some of the main features of MBR, tailored for industrial wastewater. Then we'll focus a little bit on membrane configuration. We'll discuss about what will be the objective, what will be the advantages, disadvantages. We'll touch a bit about membrane models, hollow fiber, flat sheet, tubular, which are suitable for which configuration. Then there's some of the probably best practice, I call it here, in MBR operation. So how to run our biological process and how to see it in the membrane filtration perspective. Lastly, I will offer you some of the case reports on MBR implementation in different industries. So I list here food and beverage, pulp and paper, pharmaceuticals, and also petroleum industries. I will close with some of the concluding remarks. So if you hear the, I had to, okay, if you were here last time, so this is basically the basic summaries. If you want to summarize in one slide, probably this is the best summaries. So, how if I have effluents, it's industrial effluents, and currently I am using the activated sludge process, and I want to convert it into MBR. Okay. Okay. So the capacity and the current capacity is 360 cubic meter per day, and it has an inlet BOD of 1,500. Everything is fine. I mean, my process went well. So my outlet BOD is just 20 milligram per liter. Okay, that is the current situation. And then I operate the system using the conventional activated sludge. We operated at MLVSS at about 3. I have a perfectly good sludge. So it has good settling properties. We have 10 milliliter per gram of the volume of the sludge, SPI. And then the sludge retention time is about 8 days. Basically, these parameters are all good if you run an activated sludge process. So as you can see here, so we have a loading of around 550 kilogram BOD per day based on these properties. And then I have to run the reactor at 400, so the reactor has need to have a volume of 450 cubic meter. So this is the HRT, and the SRT is like what I said. So if I would like to convert the system, I mean, I'll use exactly the same volume of the tank. So I use the same volume of the tank, and then I'll see here I fix the volume. So what can change? Can I increase the capacity? So what will be the main differences? Okay, I make a summary here. So I redesign the system. Instead of using activated sludge, using exactly the same tank, we'll use the clarifier to replace the membranes. What we are going to do is very simple. Okay, MBR allow us to operate at longer HRT. So we set HRT instead of 8 days, like here, 8 days. We set HRT of 30 days. Another fundamental difference is that now instead of running MLVSS, so MLSS of 3, I will run MLSS as 8. So what happened? The main difference if you look carefully into the layout of the activated sludge below over there, so you'll see that I fixed the same volume right here. So the same volume can treat more of the feed. So it's like 35% more of the feed. So basically, without doing nothing, without changing the dimension of the tank, I will be able to easily increase the capacity of the system by 35%. Okay, and then another important thing is that now, so previously we produce about 480 kilogram per day of sludge. Now I produce about 250 kilogram of sludge per day. It is correspond to less production of sludge by factor of 47%. So if you want to get the file of how I calculate this one, because probably you want to validate yourself, you can scan this and you will find it online. I put it in Dropbox and it is open access. So for treatment of industrial wastewater, so what are the things about MBR? So how do I know that if I can use MBR or not? The very simple things, the very simple rule of thumb is that if you currently have a biological treatment, either treating filter, activated sludge, or any biological treatments employing biology, you can convert it into MBR. And at the same time, you'll be able to improve the performance of your system. If you use MBR, okay, the system will be more resistant to variable loadings because I don't really care anymore about the settling properties of my sludge. And then I will have no worry at all about the sludge bulking. When you have a sludge bulking, then typically you won't have you won't be able to run your system at a full capacity. You will reduce the capacity, and then sometimes you have to shut down the operation because of you always have carry forward sludge to your effluent. Another thing is that more resistant to the persistent organic chemicals. This is especially true when you have pharmaceutical wastewater, phenolic compounds, and we have pharmaceuticals, especially in pharmaceutical. You have the solvent that next to the wastewater. We have a term called biorefractory or something. So basically, some of the chemicals that is hard to treat. You can imagine about having a drug mean that you need to poison the microbe in your body. For example, antibiotics. So when you have an excessive amount of antibiotics in your wastewater, it is also hard to treat. One of the things that you can look for is that you will reduce the production of sludge. So when you have a wastewater that has very high organic loadings, then converting your system into MBR is one of the attractive incentive. So because you will be able to minimize the cost handling by about 50%, as you can see from my previous slide. And based on that, if you're really doing the calculation, then maybe you will be able to offset the cost of membranes. Okay, and then as I told you before, and I will show later on, then there are so many established MBR for industries. So basically, you ask me what industry you're working on, I'll be able to find you case studies reporting the success of MBR in creating those kind of industries. There is a website that I will recommend. Some of the results I will show later on. I simply take it from this website. This website is run by Professor Simon Judd from Cranfield University. He's one of my colleagues in the past, currently also running a consulting companies on MBR. And then this paper is also useful if you would like to go in deep about the progress of membrane bioreactor for industrial wastewater. So for treatment of industrial wastewater, MBR have been applied to treat effluents in number of industrial sectors. So I'm following the classification from MBR side. So the food and beverage I'll discuss later on. We know that this kind of industry typically has very high organic loading. Okay. Petroleum industries, including exploration, refinery, and petrochemicals as well. We have pharmaceutical industries. We'll discuss a bit later on. Pulp and paper industries. Typically, this wastewater has a very high level of COD, BOD, and suspended solid. So normally it has a multiple process, train of process for the treatment. Textile industry effluents. I won't give a detail about this one. Leachate and shift effluents. So these are a list of application of MBRs that you can actually find a case report on the MBR side I mentioned before. If you are working at any particular industries and you would like to have some of the case study about implementation of MBR, you can contact Mr. Chu or Mrs. Ian, and then I'll have to find out. Because I have been working here for quite some time, I know people. If I need something, I can just shoot an email and I will get a response. Okay, so what is the main feature of MBR in industrial wastewater treatment? In my previous slide, I show you the basic question. So what happens if I convert my current tank into the MBR, and then you find out that you can increase the capacity by 30 to 40%, and then you can you can reduce your sludge by almost half. So now, to show the contrast between to show the contrast on MBR with for industrial wastewater, because industrial wastewater is characterized by very high organic loadings. On the other hand, if I have the municipal MBR plants, it has high hydraulic loadings but lower concentration of effluent. So I have two systems. So both has the same loading. Oh God, I think I sent you the wrong file. I think I mistyped it. So in one side, I have a low organic loadings. Maybe I'll just. Sorry. So what is the name of the website? Paint. Okay, I'll just snip around. Sorry. So you will have easier to compare there. So I'll just copy it from here. So basically I'm sorry, I copied this. Okay, what you can see here is two exactly same MBR. Yeah, the same MBR. The difference is that on the top it has low concentration of COD. So basically you have a high hydraulic loading, 500, and then on the and then it has a low concentration. So the loading is basically the same. So organic loadings is here I set the same, which is 200 kilogram per day. You can see here, and then the one down here is 200 kilogram per day. So what you can see here, you have to focus on this side, okay, the membrane side. So you'll probably produce the same amount of sludge. You see here, about the same volume of the reactor. Okay, the same volume of the reactors. Basically, the volume of the reactor is to compensate the organic loading. So if you have two different wastewater, but different concentration, but in the end they have the same loading, then you'll have about the same about the same volume of the tank, about the same amount of the excess sludge production. The big difference I want to highlight is that you will have a much smaller membrane area. So basically, when you look into this perspective, if I have an industrial wastewater, I'll be able to have lower membrane area because of the lower loading. And then I can then operate the system at a low flux to sustain the operation better. So if you want to go into the Excel file that I used to plot this one, you can scan this guy, and then you can get it online. So the main feature, I'll mention it again, is that tank volume will compensate the organic loadings. So it's really a function of organic loadings. If you have the same organic loadings, you will have more or less the same total volume of the tanks. But then if you have a high strength wastewater with a very high COD, we will have less of membrane area. So it's more attractive for using MBR, because now you will invest less in terms of the membrane area. So let's move on to the next one. It is about Mbr configuration. I think all of you, if you go Google MBRs, you will find out these pictures. So there are two ways of combining membrane into bioreactors. You can immerse the membrane. So as you see here, it's immersed inside, or you can put it outside here. You can put it outside. When you immerse the membrane, we call it Mbr Mbr or Submerge Mbr. And when we have a membrane in the outside, we used to name it a side stream Mbr. So what are the features of these two configuration? Submerge Mbr, you place the membrane in the aeration tank or in a membrane tank. Okay. Most of the installation they have in a separated tank, so it's in Mbr tank. So basically, if we have an activated sludge system with sedimentation tank now, we can use the sedimentation tank as the membrane tank. So no need more investment for membrane tank. The main feature of this kind of membrane is that from once or twice a year, you will need the chemical cleanings. Okay. So if you put it in the membrane tank, okay, if you have two separate tanks, then you will be able to just stop the pumping, circulation pumping, and then you can clean it in that tank. So if we have a system that is combined, so you put the membrane in the aeration tank, we will have to take it out, the membrane, and then do the cleaning outside. So that's the difference. And then this kind of system is normally operated under vacuum. So it's negative pressure, and typically the range is from probably zero. Just because from the hydrostatic pressure to up to negative 0.3 bar. Because of the low pressure, then the operation is at relatively low flux. Low flux then means you have a high investment of the membranes. However, this membrane, you can employ a module with a high packing density, which is the flat sheet and the hollow fiber module. I will return back to this later on. And then we can control the fouling through the membrane blower here by using the air to sustain the operation and maintaining the resistance of the filtration about constant over time. So in another hand, when you have a side stream configuration, okay, when we have a side stream configuration, we place the membrane externally, we have a better picture later on, and then the cleaning is done externally, so it will be easy. Okay, the main feature is that this membrane can operate 10 times of the flux of the submerged Mbr, because we run it at very high cross flow velocity, up to 3 meters per second, in some of the cases, and then the pressure of almost 10 times as well higher than the one in the submerge. Okay, and then so to my best knowledge, so far only a tubular membrane that is used in side stream configuration, and the fouling control is conducted through cross-flow velocity and using some we call as air lift. I think if you are interested in fouling control, we have another talk later on. It should be okay. So these are might be better illustration of the membrane system. So when you have a submerged system, you have here the buffer. So the thing that spacer that space the two tanks. So basically, this is two separate tanks. So operated under vacuum, you will find out that this is the vacuum. Okay, and sometimes it's for cleaning purpose, you have this kind of arrangement. So we have pump for backwashing. Okay, this is a submerged, and then a better illustration of the side stream probably will be this one. So you see how we also have a pump for backwashing, we have permeate pump. This is the feed pump for recirculation and so on. So yes, simple, basic. Then you ask me which one is better. Well, it will be a little bit hard. Which one is better? If you come to company like Kubota or Torre or maybe Suez, they will say that okay, go for submerge. Submerge has low energy, blah 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 blah. But if you go to a company that produce MBR with a side stream, they will say that no. They will say that side stream is much better, and then you have to go for the side stream. I'm natural. I think let's the money talk. So if you have any interest in converting your system to MBR, we can help you to choose, and then we can do some of the techno-economic analysis, how much membrane you will invest, the pumping, and so on. You can contact Mr. Chu, so we can help with that. I guess. So next we look into the Mbr membranes. So we have three typically. We have a flat sheet, module elements. I'll have a lot of picture after this one. Then we have this hollow fiber bundles. Okay, and we have the side stream MBR. This one is from Pentair X-Flow. And then you have a tubular membrane. A tubular membrane is like a tubes. It's like water pipe. Yeah, it's large in diameter. That's the reason why. So, and then this membrane is only applicable for side stream MBR. This membrane is only side stream MBR. To my best knowledge, working on MBR since 2005, so almost 15 years. All of the side stream tubular membrane is used for the side stream. Okay, the good thing about this one, you see it in the previous slide, is that we can operate it at very high cross-flow velocity, so less fouling, high pressure, 2 to 3 bar. Sometimes even can go up to 4 bars, resulting in quite high flux. You can have 100 and so on. The problem is that it has low packing density. So basically, we need a lot of space for this membrane. Because of it is detached from the tank, it makes it quite easy to clean the membrane if you eventually need to do the chemical cleaning. So that's the plus point. The minus point, the minus point will probably be the price. I think because of you have a small packing density, you'll need a lot of modules. Because in one of the modules here, I don't know how much membrane area you can put in. Okay, might be just 40, 50 square meter in one of the casing like this one. On another hand, this type of hollow fiber module can have almost 10 times more membrane area compared to the one in the tubular. So next, I move to Submerge Mbr. To the hollow fiber. So hollow fiber membrane is used in the submerge configuration. It has characteristic of very high packing density. So what is the packing density? It is basically the total area of the membrane mounted in the module divided by the total volume occupied by the modules. So when you have a very high packing density, it means that I can put a lot of membrane in a small space of confined in a small space of module area. So we like it, this one, especially when we have mega million cubic meter per day of wastewater treatment capacity. So if you check one by one, you will find out that most of the installation of the very large scale, they opt for a hollow fiber membrane. Okay, and the problem with this one is a little bit difficult to clean. I'm going to show you some of here later on. And then another one is the flat sheet models. It is used exclusively for the submerged configuration. The packing density is rather low, still higher than the tubular, but considered as much lower compared to the hollow fiber. The good thing about this membrane is it's allow good fluid dynamics in the modules. When you have fluid dynamics in the modules, it foul less. Okay. So if you ask me about now that we have two parameters in the equation, shall I go for the submerge or shall I go for the side stream? And then which membrane I need to use? Is it a flat sheet, a hollow fiber, or tubular? Well, really, very hard to select which one is the best, because if you go to the supplier, they will always say that they have the best model. But in our case, we are open to any of the configuration. They have a plus and minus point. And I think the best way to assess which one is best is to look into the case-by-case basis. And I think in the end, we need to do some of the economic evaluation to really answer which one is the best. Generally, you will have a balance. When you install a system with a high capex, high investment, normally we try to compensate operation. So we try to have a less complex operation. Then basically the way to compensate is you go for capex, high investment. If you want to press on the investment, say I want to invest as low as possible, then most likely you will suffer from the cost of the operation. So this is how we can see it. So, well, there must be a trade-off. That's why we have to do the analysis on case-by-case basis. Okay, this is an example of a hollow fiber membrane that is heavily folded. As you see here, you see a membrane that has what we call as sludging. The reason why is that it is very difficult to get a homogeneous aeration on the hollow fiber membrane. So when you do aeration from the bottom here, you do aeration from the bottom there, then somehow the bubble cannot travel easily around the edge. When you have this, so you got the problem like this. So basically, this kind of picture, it is very popular when you see the presentation of companies from Pentair or from Mbr Membrane that sell the cross-flow configuration. We also have on here Spectra's, the one that managed by Spectra. This is after 1 year. You will see down there on the left side. Okay, I don't know if you can see it. Also have a problem at the close to the potting edge of the hollow fiber. That is one of the main problem. Currently, then you have a different kind of flat sheet membrane. On the bottom side, this one is the module from Ecologic. You will find out that how all of the plate here, so this is a plate and frame membrane installed together, and then each of the plate, okay, is connected to the permeate line. Now you can imagine that actually the cost of the system is not from the polymer itself. So the cost of the plate and frame MBR or flat sheet MBR is coming from the support materials, from the frame. If you ask a quotation in any company, you'll find out that the cost of the flat sheet MBR compared to the hollow fiber membrane is slightly expensive, maybe almost 1.5 times of the hollow fiber membrane. So the old style of the membrane model, you have a lot of frame like this one. But if you look at if you look at the big companies like Alfa Laval, for example, here, then you will find a kind of Lego style models. So it's like an IKEA stuff. So where you can add a block by block of the elements. So this is one of this one called probably one elements, and then you can install a few elements in one skid, one frame. So in this skid, in this frame, you install two. Here we install two of the larger module area and so on. And then even if you, so I recently see these models in action. Actually, Kubota installed one of the pilot in UTM. So they have a Lego style of flat sheet membrane assembly, where you can easily install block by block of the membrane, and it is with interlocking. You see the interlocking here, so all can be connected together and installed easily. So this is a quite new development of flat sheet membrane. And then one of the advantages, I show you a slide from Tubular Membrane. So the good thing, so this is why flat sheet membrane is good. So you can see very good dynamics. So the air bubble is not only do the aeration, but it's also promote the circulation of the liquid from outside inside. So the circulation of the liquid then help to clean the membrane while it perform the filtration. So you see here there are so many different so you'll see that this is a new development of models with a good bubble distribution. This is typically of how the current flat sheet module is installed. You see that this one is wafer, basically try to adjust the air bubble to go to be well distributed along the modules. So we'll have a very nice fluid dynamics in the modules that help to clean the membranes. This is only possible for the flat and sheet membrane, which make the flat and sheet membrane operate with less fouling. Okay, operate with less fouling of long-term operation. Okay, also we have here the Xevi hollow fiber. This is now produced by Suez, I guess, the name of the company. But I think the technology has been there with Xenon first, then bought by GE Water, then now bought by Suez. This is one of the most probably popular membrane Mbr producer. They have, you can imagine this one, a small rod of about probably 1 cubic meter. They can install like 500 square meter of membrane. So a lot, packing density is very nice. And you can see that how we try to improve the cleaning by allowing the bubble to distribute well. So the other one from Xevi hollow fiber, and then you can also find some of the membrane from Puron here. This is from Koch company. They have a module that is only glued in one side. So it's a one side coating, and then the one in the end is basically loose here. So that's allowing the membrane to keep moving, and then you don't have a sludging problem typically faced by this kind of module configuration. Okay, then these are some of the, if you give you an idea about the external the external configuration with tubular membrane. You have an airlift penta-tubular. They call it mega block, a large block. You have this big installation. We also have the one from Berghoff, tubular membrane, also from Pure Aqua. So this looks like a reverse osmosis element, but actually it is an Mbr for treatment of reverse osmosis process. So you got three kind of the models. You have seen some of the picture. You know more or less about which one is better. They have advantages, they have disadvantages, and so on. So next we can move on to the best practice to operate the MBR. So the first thing is that a membrane has a less thing to do with the biology. What it means is the degradation of the pollutants is basically a job of the microbe. So we to be able to have a good degradation, we have to take care of the biology. We have to take care about the biology. So it is responsible for the organic removal. Basically, we need to maintain the operation stable, organic in terms of organic loadings and also hydraulic loadings. We need to maintain the ecological condition that is good for the biology. For example, we need to maintain the DO still high, like 1 to 2 milligram per liter. And then stable. And then typically we want to have a sludge that easy to filter. We call it good filterability. And the simplest way to look into this one is by using SVI, sludge volume index. So basically, when you do the MBR, then people will say that the best thing that can happen to MBR is actually the best thing that can happen to activated sludge. So basically, if you are an operator of activated sludge system and then you want to run MBR, just do the same. In terms of biology, just do the same. You need to maintain the system to be stable. You need to maintain the aeration. You need to maintain the loadings to be stable, and so on and so forth. Okay, the second aspect in operating MBR is the filtration itself. Okay, so the job of the membrane in MBR is basically just to separate the solid, which is the microorganism cell. And then in all of the full-scale application, MBR is operated at constant flux operation. So basically, we want to maintain the flux stable over time. Okay, so then it is important then also to, the same as the biology, it is also important to maintain the filtration performance. We call it as proper membrane fouling control. I'll get back into this one later on. Normally, we have different, we have a different stuff to do it, the different approach. The most important approach is you need to select the right flux. What is the right flux? You see here three systems. So TMP here stands for transmembrane pressure. You can check. I take this one from one of the very nice paper, journal paper. So you see that we have three experiment number 1, experiment number 2, and you have experiment number 3. So stable operation means a stable pressure. Okay. So as you have fouling, you increase your pressure. Okay, you increase your pressure, and then that is not good for MBR. You see here that if I go for the low fouling, if I go for this is a low flux. This low flux, and this is high flux. So if you go at low flux, I'll be able to maintain the operation about 1 month before the pressure goes up. If I have that kind of situation, means that my performance is more stable. The problem is that it is flux is inversely proportional to the membrane area. So if I operate at, for example, flux of 10 instead of 20, I will need a membrane of twice of the one I used to run the system at 20 LMH. Okay, then there are some of the things. So flux is one of the important things to look into when you run design the MBR. So we have some of the experience working with MBR in Malaysia, and then we noticed that they are overconfident in the flux. They design flux very high. So when you have a very high flux, you have an increment of pressure very fast, meaning that you have to clean very often. Then basically you gain in the investment of the membrane. I need to invest less of the membrane area, but in the end, I'll be very busy and spending a lot of money to operate the system. So it has to be the balance, okay? It has to be the balance. You have to think very carefully. If you ask me if the investment allow you to go, I can guarantee you that lower flux is always better. And then even recently, if you look into research now, people mention about the membrane without cleaning, basically just aeration. So we don't need maintenance cleaning, we don't need intensive cleanings. By simply run the system at flux of about 10 liters per square meter per hour. Of course, this is like probably half of the current suggested flux in industry. Basically, it means you need to invest more. But as the membrane price getting lower, that should be less of the problem, especially when you run MBR at low capacity, like a few cubic meter per hours. Another important thing is this one. I will dedicate a special slide for this one. Is it's very important to monitor the transmembrane pressure at the permeate side of the membrane. That is basically the indication of how stable is the performance. So when you have a system initially, when your membrane is still clean, so I will just write here, this is a clean membrane. This is a clean membrane. When you have a clean membrane, so we always have a low pressure. You see here pressure is very stable in the beginning, but as a function of time, you cannot have operation continuously the same. You start to have fouling, a blocking on the surface of the membrane, and you see that the pressure start to go up. Okay, and then if you continue operation, then the pressure go up even more. And then at this point, maybe you cannot continue the operation because of if you continue, then you will not get the flux the way you want it. So sometimes if you operated at too high, too negative vacuum, your pump cannot suck the water, you suck air because of that. That's why it's also not advised to run the system above probably minus 0.4 negative and minus 0.4 bar. So this is the phenomena of the dynamic of the pressure as function of time. Of course, this is because of the fouling. I will not discuss here. So to manage fouling, I'll try to speed up a bit. To manage fouling, we have many cycles. We have to run the cycle under what we call as a filtration cycle. So we have a relaxation and backwashing. The cycle can be about 10 minutes, depending on the company. And then every month, every 2 weeks, we do maintenance cleaning using a low concentration of chemicals. And then every once a year or twice a year, we have this intensive cleaning. So we have 3 types of cleaning: physical cleaning, maintenance cleaning, and intensive cleaning. These are the cycles. On top of this one, of course, we have the aeration of the membrane as the main way of controlling the fouling. So if you translate the cycle into the pressure, it will look like this one. So you'll have an increasing pressure during the cycle here. And then you do the maintenance cleaning here, maintenance cleaning here, maintenance cleaning here. So this is basically simply 1 month, 1 month, 1 month, 1 month, 1 month, 1 month, 1 month. Then we reach what we call as the threshold pressure. So basically at this pressure, you say that you cannot sustain the operation. We have to clean it. So then we do what we call as we do the intensive chemical cleaning. This one is your intensive chemical cleaning, maybe after 1 year of the operation. Then at the end of the 2nd year of the operation, at the end of the 3rd year of the operation. And then if you notice carefully, your baseline here keep increasing. When your baseline here go increase up to this point, maybe you say that, this is after 5-6 years, now we have a permanent fouling to the membrane, we cannot continue operation using this membrane and you have to replace it. So this is basically the life cycles of the membrane when you install it in an MBR. Another important thing is that we have to closely monitor the system to operate under the ideal condition. I noticed that some of the operator, they don't know so well of how to operate their MBR, so they run at quite low, for example, MLVSS. So ideally, for MBR to gain a really good advantage, we run it at MLSS of 6 to 10 gram per liter. Okay, so then you can get the full advantage of it. Then you can have the highest loading, the highest loadings, hydronic loadings, and at the same time you produce probably less sludge, because when you have a lot of microbes in the system, you have to feed them a lot with the food for the oxidation, and you produce less sludge. A lot of things I just gave it here. You look into it, what will be the ideal BOD to MLSS ratio. This is the COD to MLSS ratio, and so on and so forth. You have to also take a note at what will be the dissolved oxygen concentration. It is very important to look into the sludge retention time here. Don't be too long, don't be too less, and so on. So this is the magic table that can help the operator to operate the MBR well. I don't know, I exceeded about 45 minutes. Shall I continue? I got plenty of slides yet. So these are a summary of some of the application of MBRs in industry and food and beverage industries. I'll go quickly into this one. You can read the detail in my slide. But the thing is, they have, each industries, they have different characteristics. They have a very high BOD and COD here with variable TSS. Sometimes when you treat wastewater from food and beverage industry, you also have fat, oil, and grease content. Also, you have a high level, can have a high level of ammonia and phosphorus. So you have to think, we cannot feed this one into our biological treatment process. So we need to do a pre-treatment. Maybe you need to have a dissolved sorry, you can have a DAF, you can have a coagulation, flocculation in the beginning for the treatment. But if you look into the case studies available, you see that the key motivation for converting the conventional process to MBR is for the water recovery and reuse. And then it's really offer cost saving. We had a project dealing with the food and beverage industries, and then we calculate if we reuse the effluent MBR, combine it with RO within 3 to 4 years, just from the cost of from the saving of the water, buying the water, we'll be able to fund the whole investment. So it's very attractive. Some of the industries is limited on the number of the water they can buy from the grid. And then some of the industries also think about the security of supply. What happened if suddenly, like a problem with the Selangor water last few weeks, they don't produce water, so basically you cannot run your plant and you stop the operation. So yeah, for the reason of the security, dissolve. Thank you, dissolve air flotation. I'm too tired this morning. I got 3 hours talk like this one. I got a training, so I'm a little bit tired mind. So my memory is not there. Thank you for reminding me. Dissolve air flotation, yes, to remove fat, oil, and grease. This is an example. There are so many case studies on food and beverage industry. So that's why I provide you with a link. Here, QR code. You can use your phone to scan this one, and the QR code will bring you to the website, which is the MBR site. But I give you one example for the food and beverage industry. Litri, this is one of the MBR contractor in China. They have been building 106 units of MBR from, sorry, this is not 2016, it's from 2006 till 2017, 106 MBRs. There's so many over there you can find. So the effluent meet the requirement mostly for the reuse, like what I said before. the effluent used for, some of them used just for the standard discharge, but most of them recently, if you look at the more recent year, like 2017, 2016, they are aiming for the direct reuse because of the high quality of the permeate, or they do it in combination of nanofiltration for the reuse, or they do it in combination of RO for the reuse. Okay, that's for the food and beverage industry. Pulp and paper, typically you have a very high solid concentration over there, and the volume of the wastewater is among the largest. Basically, in the pulp and the paper industry, we need about 55 cubic meter of water to process about 1 ton of the product. So when a company come, they produce, let's say 1,000 ton, so 1,000 ton per day, they will need 550 cubic meter per day of the water to be used. So this kind of industry, they are really depending on the water grid to supply the water, and if there is any problem, they will have some of the security issue in supplying their water. So I think it is a good time to start thinking about implementation of MBR to treat the pulp and the industrial wastewater. There's some detail I will just skip because of the time, but I will show you some of the case study. There's one case study I found in Brazil. The startup was at 2018. This is more like a small industry with a pilot. Capacity just 170 cubic meter per day. You can click this reference. It will lead you the case report of this particular unit. Most of the installation you can find it is in China again. You see how dominant China now. This is the contractor for MBR. They use a polymeric membrane. Most of so in their big project, so it's about 1.1 to 10 million liter per day capacity. They just do the direct discharge for the effluent. You can find detail in the reference here. This reference is linked. So if you click the reference, it will lead you to the site. You get pharmaceuticals. Important thing about pharmaceutical is that maybe many of the conventional, biological wastewater treatment won't be really suitable for pharmaceutical. The reason is that we have this. They call it. So you see, you have a vaccine, you have an antitoxin. You have organics, solvent, there are medicine, fine chemicals. So they have these components that is, they call it a biorefractory, that inhibits, they are persistent chemicals, very hard to degrade. That's the reason why actually the conventional way of conventional method like activated sludge is not really suitable for pharmaceutical. So when we need to deal with this kind of components, normally what they need is that they need a longer retention time and a longer sludge age, the longer of the SRT. That is where actually MBR is very good. So when you have to deal with the pharmaceutical industries, come to Mr. Chu. We can look into your case, and maybe we can have some input of how you can move forward. I mean, in the end, you can work with someone else. We'll be happy to give you some advice in the beginning. I believe that, yeah, by doing this one, we will help each other in the future. So we are okay. So you have a problem with pharmaceutical wastewater. You want to increase the capacity? Simple. Rule of thumb: you can increase the capacity by about 40%. Just to convert your current system to MBR. If you have no space to go for expansion, no worry, we can use your exactly the same tank and we'll be able to increase the capacity by about 40%. This is an example. I'll not go into detail. And then we also have MBR in petrochemicals, less in the exploration, more on the refinery and petrochemicals. What I think is that very important here to mention that we need a lot of pre-treatment because it contains some of the dissolved, some of the emulsion of oil. When that happens, then we need pre-treatment. One of the famous one is again the DAF, dissolved air flotation. We can also have induced gas air flotation, coagulation and flocculation. So it's very important. So the way to easily think about what will be the pre-treatment I need is basically what will be the pre-treatment I need if I run a normal biological process. That's it. So if that pre-treatment is enough for the normal biological process, that will be enough for the MBR. So I make a summary of some of the case study here. Here now is the project by Torre. You see, it's an Ordo city facilities in the. I think it's in the. It's treating the. I know what is in Inner Mongolia. I think it's in Mongolia. One of the process that liquefy the coal. That is the process. The MBR show of excellent performance. It has been for a few years. Here, so when Saudi Aramco built one of the city in the middle of the desert. That is the petrochemical industry. They also use Nutera MBR to treat the treatment, and the effluent is not discharged. It's even used for irrigation around the area in the middle of the desert. Can you imagine? Okay, so I'll recommend you with these two books by Simon Judd. And then if you want to look into detail about MBR, you can visit the website. I advertise this is my good friend, Simon Judd. In fact, we asked few questions recently and they were very, very happy to answer. This book gives some of the first book focus on the fundamentals. The second one, you'll find a lot of case study on industrial wastewater. More update, you can go to the website. So it brings me to my last slide, which is the conclusion. So I think it's pretty sure that based on my presentation, I can confirm that MBR can upgrade the computational activated sludge. In doing so, if you convert the current biological process, you can increase the capacity and at the same time produce less sludge. By looking into the sludge here and the production capacity, so it opens up the possibility of the existing process to be converted to support the plan for plant expansion. If they want to expand by about 50%, we are quite sure we can still run the wastewater treatment system by using exactly the same facilities and by converting the facilities to MBR. Okay, they are based on the configuration. We have Mbrs, submerged, and then you have three types of membrane. You get a flat sheet, hollow fiber, and tubular. And when you run MBR in operation, we have to look into the biological process, the filtration process, and close monitoring on membrane fouling management, and then how to do it, which flux you want to run it, how often you want to clean it. It is case by case basis. So you can contact Mr. Chu, and then we can help you to some technical advice. Lastly, I want to state again that MBR has been well established as a proven technology for various industrial wastewater treatment. So normally plant manager in Southeast Asia, in China, as long as we don't see a success story, we don't want to go it. But for MBR, I assure you that I can find the exact plant, exact MBR like the industry you are running on. And then just to convince you that there are case study, there are success story about MBR application for that particular industry. So I think that's it. This is like from my old slide. So I end up my presentation here. If you have any question, I'll be happy to answer.
Okay, thank you, Dr. Roy. So now we have one question. Is from Jeffrey. So what is the impact to the membrane exam? For example, the incoming BOD is designed for 250 milligram per liter, but the actual incoming BOD is less than 100 milligram per liter. Is it difficult for the MLSS in aeration tank to maintain as 6,000 ppm? And what is the other impact to the membrane?
Okay, the main impact will be on, because your loading is lower. So basically what happened, if that happened just one day and incidentally, like 1 day or 2 days, and then revert back to the design loading, that should be no problem at all for MBR. So if the problem is persist for a long time, meaning that now your F to M ratio, food to microorganism ratio increase. In that case, your microbe will starve. Okay, they are out of food. When they are out of foods, the first thing they will do is they will break the flock, make it smaller. Then you will probably have a problem with membrane now. So you have to, instead of dealing with flock, you are dealing with a smaller flock. Another indication will be there if the problem persists, what will happen is your microbe will eat cannibals, endogenous respiration. They will eat others. Okay, this is what happens when you have a too low food to microorganism ratio. The implication for the quality is almost nothing. It is just that probably your flock dynamic will change a bit until you restore the condition to the normal design. And then of course your MLSS will go down a little bit, but MLVSS of lower is probably less of an impact than when you have MLVSS of higher than design. The problem won't be on the membrane. Okay, your filtration will be as good as at 6 or at 10, but then the problem later on, when you have very thick sludge, we will have a problem in maintaining the dissolved oxygen.